Hi everyone, in this video we're going to look at large carrier amplitude modulation, which involves an asynchronous or non-coherent demodulator as opposed to a synchronized demodulator as in suppressed carrier amplitude modulation. In large carrier amplitude modulation, a baseband signal x of t, such as an audio signal, is DC biased by adding a constant a to it before modulating by the carrier signal. So x of t gets added by a DC constant a, and then modulated by cosine of omega ct. So the modulated output, which is what gets outputted from the transmitter, in this case is y of t equals a plus x of t, that whole thing times cosine of omega ct, where omega c is the carrier frequency of our station. And this constant a is chosen such that a is greater than or equal to the maximum of absolute value of x of t, which means that this quantity here, a plus x of t, is greater than or equal to 0 for all t. Now let's look at how we can demodulate y of t to obtain our original signal x of t. Since a plus x of t is greater than or equal to 0 for all t, by putting y of t through an ideal envelope detector, we would get at the output simply a plus x of t, because an ideal envelope detector would return absolute value of the envelope, but since our envelope a plus x of t is greater than or equal to 0 for all t, our envelope detector would simply return a plus x of t. And just to review, the envelope detector circuit is given by an input voltage, in this case y of t, a p-n junction diode, and then a resistor in parallel with a capacitor, and the output voltage is taken as the voltage across the capacitor. There were 4 conditions that had to be satisfied for the envelope detector to work properly. The first was that the envelope is non-negative, which is satisfied since a plus x of t is greater than or equal to 0 for all t. The second is that the envelope changes much more slowly than the carrier itself. This is definitely satisfied, since if we're transmitting an audio signal, which can be considered to be band limited at 5 kilohertz, but in commercial AM radio, the carrier frequency is in the AM radio band, which is between 530 kilohertz and 1610 kilohertz. So definitely the carrier frequency is much greater than the maximum frequency of the envelope signal. Therefore, we need the third and fourth conditions to be satisfied, which are RD, the forward resistance of the p-n junction diode, times C is much less than 2 pi over omega C, which means that the response time of the envelope detector when the p-n junction is forward biased is much shorter than the period of the carrier. And then second, 2 pi over omega C is much less than RC, which is much less than 2 pi over omega B. So the response time of the envelope detector circuit when the p-n junction diode is reverse biased is much longer than the period of the carrier, but much faster than the rate at which the envelope changes. Assuming that the envelope detector behaves ideally, the output of the envelope detector would be exactly a plus x of t, which means that by adding a DC blocking element, we would cut the DC component of this incoming signal, and we would obtain the original signal x of t. Now, the only drawback of large carrier amplitude modulation, which is seemingly a lot better since it's asynchronous or non-coherent, is that if we look at the expression for y of t, we have y of t equals a plus x of t times cosine of omega ct, which equals a times cosine of omega ct plus x of t times cosine of omega ct. Now the part of y of t that equals a cosine of omega ct doesn't carry any information, but we still need power to transmit it, so large carrier amplitude modulation isn't as power efficient compared to suppressed carrier amplitude modulation. So this term here, a cosine of omega ct, is what makes large carrier amplitude modulation less power efficient since it requires power to transmit this term even though it doesn't contain any information. Alright, so this is it for this video, And in the next video, we're going to take a look at commercial AM radio and the famous Superheterodyne receiver, which is an application of the large carrier amplitude modulation scheme that we saw in this video.